Okay, guys, you thought you could escape physics, but not quite. So I want to do a couple of small videos just so that we can finish off the homework associated with Module 14. And the juniors, you're going to have a small opportunity on that module as your final. So we're dealing again with the voltage that uh, takes place between a moving charge and a stationary charge, and at two different positions. So we look at the change of voltage depending on the distance between those two charges. That allows us to look at the change in potential energy, and then likewise we can relate that to kinetic energy. So we're going to go over example 14.4. I'll run through it. We'll do an on your own example of it. Then there's another problem kind of going in the opposite direction in 14.4, and we'll look at that too. But here is our first problem. It's all written up there. And we have, in this case, we have a negative 2 microcoulomb charge. Here it is, small q, because this is the one that's moving. And we're given that its mass is 1.44 kilograms. And it is placed this distance, the initial distance from the stationary charge is 1.5 meters. So it's placed 1.5 meters from our stationary charge, which in this case is a positive 1.8 times 10 to the negative 3 coulombs. And it says if the particle starts at rest, how fast will it be moving if it has traveled, okay, to this final distance? Starting here, going here, how fast is that particle going to be moving given these conditions? So the first thing we have to do is calculate the voltage at the initial position. So here is Coulomb's constant, again, times the stationary charge divided by the initial distance between the two charges. And so here's the voltage between the electrical potential between those two charges at that distance. Then once it has moved, we want to calculate the same thing. So there's the number of volts between the two charges at that final position. Okay, so we have those two things. That allows us to calculate the change in voltage. And notice that it is the final voltage minus the initial. It's the final minus the initial. So we get 1.1 times 10 to the 7 volts. With that, we can calculate the change in potential energy. And here, when we're looking at the potential energy, we're dealing with the charge of the moving particle and not the stationary. So far, up here, when you're just calculating the voltage, you're only concerned with the stationary particle. But down here, okay, as we fill this in, so here's the moving particle's voltage, and the charge on it, and here, of course, is the change in voltage. Okay, and so the change in potential energy is negative 2.5 times 10 to the fourth joules. All right, so look, the potential energy has decreased as these two particles have moved closer together. Okay, and if the potential energy decreased, that means by this amount, that means the kinetic energy increased by that amount. So in this case, we're asked to calculate what is the speed, the velocity of that particle once it reaches this destination. Okay, so if we manipulate this equation to solve for velocity, here it is. And again, notice that the kinetic energy, okay, again, if potential energy dropped by this, kinetic energy increased by that same magnitude. So there it is. So if I manipulate the equation, the velocity is going to be the square root of 2 times the kinetic energy divided by the mass. I put it in, and I find out that that particle is moving at 190 meters per second once it reaches this position from the stationary charge. Okay, so that's the first part of exercise 14.4, where we're looking for the velocity of a moving particle in relation to a stationary particle. All right, so similarly then, on your own, I know it's hard to read from the glare, 14.5, here's a good example, because you'll find something very similar to this amongst the problems that you have to do in the practice problems. All right, so here is our criteria this time. So we have a stationary charge of 3.4 coulombs positive. we have a moving charge of positive 6.5 coulombs. Here's the mass of it, of that moving particle. Initially, they're 1.4 meters apart, and evidently they're moving apart. And so the actual wording of it is we have a 6.5 coulomb charged particle of mass 42.3 kilograms is placed 1.4 meters away from the stationary charge. If it starts from rest, how fast will the particle be traveling when it is 2.5 meters away from the stationary charge? Okay, so there's not any difference in the procedure from the example here. So we need to calculate. So notice in each one of these cases, if we're asked to find the velocity of the moving particle, then the first thing we're going to do is calculate the initial voltage. Okay, Coulomb's constant, the stationary charge, the initial distance between them. So we get 2.4 times 10 to the 10th volts. Then we calculate, okay, the final voltage. So there it is. Okay, so at 2.5 meters, same thing we did here, 1, 2. The third thing that we're going to calculate then is the change in voltage. So it's the final minus the initial. So notice that we have negative 1 times 10 to the 10th volts. Then that allows us to calculate the potential energy. And here is where we use, okay, the charge on the moving particle. Okay, so that's where small q comes into play, lowercase q. So 6.5 coulombs times the change in voltage, and that results in negative 6.5 times 10 to the 10th joules. So this tells us that the potential energy decreased by that amount. That means the kinetic energy increased by that amount. So if this is negative, this is positive, same magnitude. Just like over here, we had a decrease of this, so we had an increase of the same magnitude amongst the kinetic energy. All right, so that being the case, we can calculate then the velocity using the kinetic energy equation. We manipulate it, and it's going to be the square root of 2 times the kinetic energy divided by the mass. And so we find out that at this position, that moving charge is moving at 5.5 times 10 to the 4th meters per second. Okay, so there's that situation. And again, that'll allow you to do some of the problems that are in the practice. I'm going to erase this. I'll come back with another video showing you where we're working really backwards from here back instead of from here in this direction.